Imagine falling into a black hole. You are getting closer and closer, but something strange is happening. The stars around you are no longer where they should be. Their light is bending around the darkness ahead. And then comes the part that sounds impossible. You can cross the black hole's event horizon without feeling anything at all. But someone watching you from far away will never actually see you cross it. So, which one of you is right? To understand that, we have to follow the fall from the very beginning. First, forget everything you have seen in movies about black holes sucking up entire galaxies. A black hole is not a cosmic vacuum cleaner. It is a region of space-time where an enormous amount of mass is concentrated into an extremely compact region. Its gravity becomes so intense that beyond a certain boundary, nothing can escape back to the outside universe, not even light. And black holes come in very different sizes. A stellar mass black hole can contain roughly several times the mass of our Sun. But at the center of our galaxy sits something much larger, Sagittarius A star. It contains roughly 4 million times the mass of our Sun, and that enormous difference in size completely changes what happens when you approach one. As you get closer, the first thing you notice isn't the gravity, it's the sky. The stars begin appearing in strange places. Their light curves around the black hole before reaching your eyes. This is called gravitational lensing. The black hole is bending space-time so strongly that even light cannot travel in a simple straight line near it. And if the black hole is surrounded by an accretion disk, things become even more spectacular. The disk contains incredibly hot material orbiting at enormous speeds, but you wouldn't see it as a simple glowing ring. Gravity bends light from the far side of the disk over and around the black hole, so you can actually see parts of the disk that would normally be hidden from you. The closer you get, the stranger the universe looks. And then gravity starts affecting something much closer to you, your own body. Your feet are closer to the black hole than your head. That means your feet experiences a stronger gravitational pull. The difference between these two gravitational forces is called a tidal force. Near a small black hole, the difference can become enormous. Your body will be stretched along the direction of the black hole and compressed from the sides. This terrifying process is known as spaghettification. But here's where black holes become completely counterintuitive. A supermassive black hole can actually be much gentler at its event horizon. Because its event horizon is so enormous, the difference in gravity across your body can be relatively small. You could potentially reach the horizon without being immediately torn apart. And that brings us to the most important moment of the entire journey, the event horizon. The event horizon is not a wall. It isn't a solid surface. You wouldn't crash into it. There will be no explosion, no alarm, no sudden impact. It is simply a boundary in space-time. Beyond that boundary, there is no possible path that leads back to the outside universe. You can fire your engines. You can turn your spacecraft around. You can try to escape in any direction. It doesn't matter. Once you are inside, there is no route back out. But now comes the strangest part. Someone watching you from far away sees something completely different. Imagine someone watching your spacecraft from a safe distance. As you approach the event horizon, the light coming from your spacecraft becomes increasingly affected by the black hole's gravity. Your signals become delayed. The light becomes increasingly redshifted, and your image appears to slow down and fade. From their perspective, you seem to approach the horizon without ever visibly crossing it. But from your perspective, something very different happens. You continue falling. Your own clock continues ticking normally, and if the black hole is massive enough, you can cross the event horizon without encountering any physical surface. There is no magical moment where your body suddenly stops. You simply continue falling. So how can you cross the horizon if the distant observer never sees you cross it? This isn't a contradiction. It is one of the strangest consequences of Einstein's theory of general relativity. Different observers can experience and describe the same journey through space-time differently, and once you cross that boundary, one fact becomes absolute. You cannot come back. Inside the event horizon, escaping becomes impossible. Not because your engines aren't powerful enough, not because the black hole suddenly grabs your spacecraft. The geometry of spacetime itself gives you no path leading back outside. Every possible future direction you take takes you deeper inward, and as you continue falling, your view of the universe becomes increasingly distorted. Light from the outside universe can be bent and shifted into strange patterns around you, but eventually the question stops being about what you can see. It becomes a much bigger question: what is waiting for you at the center? According to classical general relativity, your journey eventually leads towards a region called the singularity. But there's an important problem. We don't actually know what a singularity physically is. The equation of general relativity predict extreme conditions where space-time curvature becomes unbounded. And at that point, our current theory can no longer give us a complete description of reality. This is where physics reaches one of its greatest unanswered questions. To understand what truly happens under these conditions, scientists likely need a theory that combines gravity with quantum mechanics, and we still don't have the complete theory. So, despite everything we know about black holes, there is a part of them that remains hidden from us. And yet, black holes are not science fiction. We have observed their effects on nearby stars. We have detected the radiation produced by matter falling towards them, and we have obtained images of the regions around their shadows. We know they exist. We know they can distort light. We know they can warp space-time. We know that crossing their event horizon means losing any possibility of returning to the outside universe. But we still don't know what ultimately happens at the deepest point of our journey. And perhaps that's the strangest thing about falling into a black hole. You wouldn't just be falling into darkness, you will be falling towards the boundary between what humanity understands and what it doesn't. And beyond that boundary, the universe still has questions we cannot answer.